everyone, in today's video we are discussing about BJT. So BJT is bipolar junction transistor. A BJT is a one type of semiconductor which consists of P type and N type between two other layers. What does that mean, between two other layers? That means for P type we have PNP and for N type we have NPN transistor, and both the NPN transistor and PNP transistor are connected with three terminals. So we can see here three terminals. So these three terminals acts as collector for P type, emitter for P type, and base is N type. Here similarly we have three terminals, emitter for N type, collector for N type. Here the base is P type. So this is a NPN transistor and this is a PNP transistor. BJT is a three-terminal semiconductor device consisting of two PN junction which will be able to amplify or magnify the signal. Okay, and then the three terminals of BJT are, as I said, the three terminals are collector, emitter, base. So the three terminals are emitter, base and collector. BJT requires an external source of DC power supply to carry the amplification process. So it requires some DC power supply to carry some amplification process. Here JE and JC is a function. So here we can see emitter to base we have a junction, that is JE, for connection of emitter to base. For base to collector we have JC junction as a connector. Similarly for NPN we have JE emitter to base junction connector, and here we have JC from base to collector connection. So BJT are of three types: fixed bias, or we can also call it as a base bias, and we have one more type, collector to base bias and voltage divider bias. So these are the three types of BJT classification. So let us see one by one. So let me first explain about the fixed bias or a base bias. We can also call fixed or base. Based bias configuration is using NPN and PNP transistor. So we are using NPN and PNP for base bias. How the circuit will differ, you see. See, for NPN transistor, the current is flowing from VCC to ground. So we can see in NPN the current is flowing from VCC to ground. See here the resistor collector where the current is flowing towards the ground, and resistor base where the current is flowing towards the ground. From VCC the current flow is towards ground in NPN transistor. So we have two resistors parallelly connected, that is RB and RC, which flows the current base and current collector. Here we have the voltage across the base emitter. Here we have the voltage across the collector emitter. Similarly for PNP, the current flows in the opposite direction. From ground to, it will flow towards the VCC. So it will flow from ground to VCC. How? See, the resistor base where the current IB is flowing, where it is taking from ground, the current is flowing towards the resistor base, and from ground the current of the collector is flowing towards the VCC. So this is the difference between NPN transistor and PNP transistor. Next, a base resistance RB is used between VCC and base to establish a base current IB. That means here this RB is using as that means here RB is used for establishing the IB current, and VCC and RB are fixed values, so IB remains fixed. So VCC and RB values will be fixed, so the IB also remain constant. The current direction is different in PNP and NPN transistor, as I said. So now for this circuit we are finding the equations. So here we are finding by using the Kirchhoff law. What is Kirchhoff law? That is VCC is equal to voltage across the base plus current flowing through the resistor base. So here we will check from VCC to VBE. First our equation is from VCC to VBE. So VCC is equal to voltage across base emitter plus current flowing through resistor base and resistor current flowing through resistor base and current IB. So this is the equation we get by using KVL law. So here VCC minus VBE divided by resistor base equals to current IB will get. Here always the VBE is fixed value. So for silicon value it is 0.7 volt and for germanium it is 0.3 volts. Similarly, we are applying the KVL law from VCC to VCE. See, in this circuit we are applying from VCC to VCE. So we are getting VCC is equal to VCE plus IC into RC. So we are getting using KVL from VCC to VCE, VCE plus current flowing through the collector and resistor across the collector. So this is the final equation we'll get, and where IC is equals to HFV into IB, that is hybrid parameter forward current gain across the common emitter.